Recording on. That means we're beginning. Hi, everybody.
Oh,
Hi, yeah. We'll pretend like I haven't been standing here for 5 minutes and we'll greet you anew. So we have a few things open to continue where we left off last time with respect to piecewise models. So the idea of piecewise, what do these models do? Let's start there, shall we? What are they for? And I got a picture up here to help jog your memory. Go for it.
based on that picture, my understanding is that here we are trying to analyze the linear trajectory using a linear or non-linear but discontinuous approach
Yes.
instead of the linear, quadratic, or cubic trend that we saw some weeks ago.
Yes, discontinuous is the idea here. So these models are designed when something changes and you want to capture change over time before and after whatever change in procedure, process, rule, etc., some sort of critical event. And each piece, as you noted, can be linear or nonlinear, but the idea is that we're breaking it into sections and hopefully being able to model an overall trajectory of nonlinear change either more parsimoniously by breaking it into sections or just to be able to answer research questions about how the slope changes in different points in time. Good. And this is an example that has 4 different slopes to it. The one we were looking at had only 2, but then we had a question in class and I wanted to redeem myself. So I totally froze in class and couldn't come up with the coding system in front of everybody, knowing that I was being recorded. And that is on the recording, by the way. I don't even edit out my own stupid mistakes. It's a faithful recollection of what happened during class. But I wanted to redeem myself. So I finished this yesterday and posted it on the website for Tuesday's class. This is what it would look like if I wanted to fit a model for 9 occasions that had 3 piecewise slopes to it. So in this example, I wanted 2 different change points, or knots as they are called. One is after session 2, so I have one slope that goes 0 to 1 to track the change from the beginning to session 2, and then it shuts off. So the idea of this coding scheme is that we don't want to go back to where we started, but we want the slope to essentially turn off its index of time at session 2, so that if this was the only term that's in the model, we would expect some kind of change between 1 and 2 and then a complete leveling off. So it's essentially, if I look at it as a dummy code, session 1 versus all the others. And that doesn't make sense if we left it that way, but that's where the other slopes kick in. So the next slope is supposed to capture change between sessions 2 and 5. And so it would do that by starting at 2 and then tracking the distance relative to 2 at each subsequent occasion, but also shutting off after 5 with a constant value so that it's not tracking change over time any further after that point. And then the third slope picks up at session 5 and goes the rest of the way. So this type of coding scheme in which the variables that you're creating indicate change directly during each period is useful for answering questions about, is there any change at all? So the significance test that goes with this slope, once all 3 of them are in the model, would say, is there significant change on average between 1 and 2? This one would be, is there significant change on average between 2 and 5? And this would be a rate per session. Likewise, a rate per session, is there any change between 5 and 9? So if that's what you want to know, this is how I would set it up. Question?
Why are we, I don't know how to ask this straightforwardly. Why are we using dummy coding for this setup?
It's only dummy coding in this case because there's only 2 possibilities because I'm only tracking change between 2 sessions. But if you look at this as a dummy code, then it really is session 1 versus all of the others.
Okay.
Because all of the others get covered by these 2 parts here.
Okay.
So a relay, did you say that
Yeah.
last time? Yeah, a relay I think is a good analogy for this. Slope 1, 2 hands off the baton to slope 2, 5. They run the next leg, then slope 2, 5 hands the baton off to slope 5, 9. It's a 3-person relay, not a 4-person, but we can make this up. So then we did a couple examples of how I could also use this model to answer questions about differences in change. And because of the way that it's coded, any question about differences in change has to be done as a linear combination of the estimated fixed effects. So I labeled then what these would represent. So if I put in a contrast of something like this into contest 1D, or an analog to this in the other packages, this would contrast how slope 2.5 differs from slope 1.2, where slope 1.2 would be the reference for the comparison because it has the -1. Likewise, this second contrast would tell me how slope 5.9 differs from slope 2.5 as the reference, and then this one tells me how slope 5.9 differs from slope 1.2 as the reference instead. And then the last one was just an example that you can use different coding schemes to combine these slopes in whatever way is of interest to you. So if I had a question about whether the average of the slopes from 1 to 5 was different than slope 5.9 that came after it, I could answer that question with this type of contrast, where the -1 gets divided into the two spots that are to be averaged over. And then I can compare that as the average slope for the two, equally weighted between the two sections versus the latter one. And where I froze was in trying to move the intercept away from the beginning to one of the not points at 5, but I figured it out. I believe that it would look like this. So the intercept is the occasion where all of the slopes are coded as 0, so that's your starting point. And then we have to figure out the change in time relative to where the slope ends. So the easiest way to think about it is probably to start with the last one. So the last one is only supposed to be active between 5 and 9, which is why it's zeroed out up to that point. And then it tracks how much time has passed relative to session 5. Likewise, the middle one is only tracking 2 to 5, and so it goes backwards in time because 5 is the reference point. So occasion 4 is 1 fewer, occasion 3 is 2 fewer, and so on. And it stays at 0 because that's where it shut off after session 5. And then the last one where I got stuck is that it needs to be relative to session 2. So session 1 is 1 fewer than session 2, which is why it's -1, 0. So the pattern is essentially the same across these different coding schemes. It's just where is the 0 as the reference for time. And you can put that wherever you would like. The why you would want to put it at session 1, say, versus session 5, because the end result of where your intercept is that you get a variance around it, right? You get a random intercept variance in your model. And as soon as you put in random slopes, what happens to that random intercept variance? It changes its interpretation from mean differences to something else, right? Intercept differences at time 0 specifically. And so that is essentially a snapshot of how people differ from each other that you can then predict with person-level characteristics. So it answers a different question if you put your intercept at the beginning in the middle. So this describes what are the reasons why people differ when they walk in the door before anything happens to them. You might want to predict baseline differences and control for that. Whereas if I had the intercept at session 5, then if I'm predicting it, it's what are the reasons why people differ halfway when they're halfway through the study. So that could be the idea of some people improving faster than others, like basically predicting who ends up higher at 5. You could put it at the end instead, and then you'd be predicting why some people end up at a different place relative to each other. So those would be the concerns that would dictate where time 0 would be most useful to you. But the good news is that through any model, you can always get the prediction at any occasion besides time 0 with your linear combination estimate statements, these sort of things. You can always reconfigure where 0 is. Question?
I don't know if I asked this last class, but why are we using the contest from D function instead of GLHT?
And you did ask that. And there are two potential answers, and I'm not sure which is correct.
Okay.
Either I tried GLHT with it and it didn't work, or I tried it with it and it didn't give me the right denominator degrees of freedom.
Oh, this is Sanford.
It needs to be Satterthwaite or Kenward-Roger.
Can you go over one more time what Satterthwaite? Yeah, this.
I would be going over it for the first time, actually, because I've only waved my hands at that up to this point. But I can give you an analogy. Where this started was actually, I think it's a 1946 paper. It's a person's last name. You know, of course, they name it after themselves or other people do. And it is analogous to how degrees of freedom changes for a paired sample t-test, I think, if you have different, I'm trying to remember it. I don't know if it's paired or unpaired. It's the one where you have different sample sizes per group and different variances per group.
Okay.
So the correction that was developed for degrees of freedom in that situation, essentially on steroids, is this. So denominator degrees of freedom in these models is very tricky because is it based on the number of people? Is it based on the number of occasions? Because occasions aren't independent. They're dependent to the extent that you have relationships, you know, of the occasions from the same person due to intercept slopes and whatnot. So Satterthwaite degree tries to estimate denominator degrees of freedom, taking into account differential sample size of persons and items, but also differential variability at each level with respect to the predictor and the outcome. Long story short, lots and lots of older simulation research suggests that if you have relatively few cases, you need to be concerned about getting your degrees of freedom right. Once you have enough, it doesn't matter as much. But in these sorts of designs, because longitudinal data are difficult to collect, you often don't have a lot of people. So it matters more to get those correct. Kenward-Roger is another degrees of freedom method, and I believe it is the default in R. When you add certain things, it just shows up that way. That starts with Satterthwaite for the denominator degrees of freedom, but then it also adjusts the standard errors for small sample bias in estimating the variances. So it tries to come up with better estimates of standard errors that are not based on asymptotics as much. And again, that's about the level of understanding I can give you off the top of my head.
It's kind of like adjusting for, like, anti-prone, like making things less prone to inflation.
Yeah, it's designed to make it so that your type 1 errors are correct. Like these are things that statisticians have figured out long ago. And it's usually used in the context of residual maximum likelihood estimation. There are rare combinations where you could do regular flavor ML and have degrees of freedom. SAS is only one of the few programs. Like in Stata, it doesn't let you have that. It assumes that if you're using ML, that you have enough people to not worry about degrees of freedom. So,
That makes sense.
yes, but that's I couldn't get the right degrees of freedom to come out unless I did it that way, is the reason I'm using Contest 1D. Okay. So any questions on this, or, and if your question is, I want to see you coded a different way, then I'm just going to say no. If you want to ask me that and I'll come back on Tuesday with it coded a different way, then I can say yes. Is that fair? Yeah. I'm only partially kidding. I like your questions. So, point being, the coding scheme needs to reflect your interests about when change should happen and when change should differ between sections. So that's usually based on the design of the study. Such as in multiple baseline types of intervention research. Okay, so that method of coding that I just showed you, the direct slopes, that's going to tell you about change during each phase as its own entity. Let's take a look at how that would be implemented. Shall we look at an example? Example 6b. Zoomers, are you with me still? Everyone's quiet in the chat. Thumbs up? All right, excellent. Excellent, thank you. So we have the same data that we played with for polynomial models, 6 sessions of response time as the outcome. And I decided, purely based on the growth trajectory, that it looked like this type of nonlinear change could be approximated by a 2-piece slope model, where the first slope reflects change from sessions 1 to 2, the initial practice slope or early practice, and then a second, more shallow slope that reflects further practice, later practice. And again, literally just based on, I think it looks like this. I'm going to make these slopes. I don't have a good theoretical reason for dividing these up at session 2 because nothing different happened. So coding then. The coding that I have here in each of the programs is probably longer than it needs to be, but I did that on purpose to make it as transparent as possible as to what is happening. This coding scheme is designed for data that are balanced. If you have unbalanced data in the online files that go with this example, I have a different type of code that would be used because you'd have to find the difference between sessions rather than just coding it as integer. So session 2 has to be at the same exact occasion for everyone in order for this to just be an integer right here. Otherwise, I would have to have that be like the time at session 2 minus the time at session 1 to figure out for that person exactly how much time has passed. Does that make sense? You're nodding. Makes sense to you? Good. So this coding scheme then right here, I've named the variables to indicate when they are indexing change. So it's not 12, it's 1, 2 to me, and this is 2, 6. So if it's session 1, then I want that to be my intercept and they're both at 0. Otherwise, for each session, then the numbers match the way that I had done it in the Excel sheet here, basically. So this is why I always make these sorts of tables first, and then I write the code that executes what the table does. And in SAS, the do and the end is necessary anytime that you have 2 statements to be evaluated, 2 or more statements based on a condition. So if session 1 then do all these things, and then end shuts off the if part here. And then else means that it doesn't have to read through every single line of the data. It skips over those that have already met this condition. So those are fairly straightforward. I'm also creating a time predictor, which is the same as we had last time, which I'll use in the second half of this example, but not yet. And I'm also creating the 6 session dummy codes that are going to be used to test absolute fit of the fixed effects to the saturated means. Since we're using REML, we can't do that with likelihood ratio tests, but we can do that by plugging in dummy codes and seeing if they contribute to the model to fully spend all the degrees of freedom for indexing average change. Stated codes do the same thing, is longer because I don't know how to do multiple things for the same conditional if. I looked for it, couldn't figure it out, and gave up. So if any of you know how to do that, and hardcore Stata users, please let me know. This is using a recode function. So I first generated a new slope variable and set it equal to the previous session variable, and then selectively recoded. So if it was 1, slope 1, 2 becomes 0. If it was 2 or higher, it becomes 1. Likewise, 2, 6 gets recoded into 0, 0, 1, 2, 3, 4. We have time as session -1. And then we have the session dummy codes, which we actually only need this many in this example, but I included all of them in SAS for reasons I now don't remember. And folks in R, again, this is the way I know how to do it. It's probably more code than it needs to, but it's, to me at least, clear what is happening. So I set slope 1, 2 equal to session, and then use this which command to systematically recode it from 1 to 6 into 0 or 1 for the first slope, or from 1 to 6 into 0 to 4 for the second slope. Then we have the time predictor, and then we have the dummy codes for the last 3 sessions that we're using to test absolute fit. So any questions on the coding idea here? Okay. So not your homework that's due Monday, but the next homework after that, for 2 weeks from now, you'll get a chance to practice this. It will be a 3-slope model, I will tell you that. All right, so then first try here. Just to remind you, here's my coding scheme for how I'm representing change over time. I'm starting with a model that has both fixed slopes in it, but only a random intercept. So this is a difference in strategy relative to the polynomial models. For For the polynomial models, I started with empty and then fixed linear, random intercept, and then random linear, and then fixed quadratic, and then random quadratic. And I did that because all of the terms are hierarchical. In this case, these two slopes are not hierarchical. They're both needed to define the overall trajectory. So it doesn't really make sense to test slope 1, 2 by itself and then add slope 2, 6 or vice versa, because they only have the meaning that I want them to have when both are in the model at the same time. So it's analogous to when you have a categorical predictor that has 3 or more categories, and you have to put all of the dummy codes for it in at once for them to mean the differences between the categories that you had intended. Otherwise, it doesn't work. But it's an open question as to whether each of these fixed slopes also needs to be random. You could have neither, both, or either. And so I'm starting with just a random intercept to provide a baseline of fit against which I can then add the random slopes and test whether they improve the model based on a likelihood ratio test. So this is a parallel change model, but it is like a broken change kind of thing. With me so far? Cool, all right. So then here are the corresponding syntax to make that happen. I'm in REML as usual. Response time in milliseconds is my outcome. My level 2 identifier is person ID. My level 1 identifier is session. So that's the original 1 to 6 variable that's being treated as an ID variable in this case. I've got slope 1, 2 and slope 2, 6 as fixed effects, only a random intercept. I am asking for the predicted mean or intercept, conditional mean at each occasion, so I can see how well the model appears to fit the saturated means. I am also asking for one slope comparison. So this idea of slope 1, 2 given a -1 and slope 2, 6 given a 1, what that's going to do is, hey, SAS, can you take the estimate that slope 2, 6 is going to have and subtract from it the estimate that slope 1, 2 is going to have and give me a estimate, standard error, and hypothesis test for that difference in slopes? Cool, thank you. Why would I want to do this? Can you think of a reason why it would be useful to know if the slopes differ from each other? These are all fixed so far. But the slopes differ from each other across people would be random effects. These are just whether the two fixed slopes differ from each other.
Whether we even need to break the slope in the first place. If the slope are the same, then we don't need to separate them.
Yes, exactly. Whether we need to break the slope into two pieces in the first place. If these two slopes are not different from each other, one would argue that a single line through the whole thing is probably going to be good enough. Now, this is on average, and it might be the case that they need to be broken in half for some people and not others, but we would get to that later. But this is something that I might report just to justify my choice of model. The slopes are significantly different, therefore we need two of them. And we have pseudo R² call here so that we can get some effect sizes. Do those in just a little bit. Here's the state of code. So C dot slope 1, 2 and C dot slope 2, 6 in the fixed effects. We have then lincoms is what I'm using to generate predicted outcomes for each session. I could do that with margins more succinctly, but this way is more transparent. And I'm also storing the results of this model so that I can do a likelihood ratio test against it in a few minutes. Our folks, we've got Elmer today because right now we're using an R matrix that's diagonal. So I had some questions about that relative to the last homework. The NLME package has functions GLS and LME that allow you to have random effects and R matrices that are something other than just variance components or diagonal. Elmer does not allow the latter. So Elmer is fine if all you want to have are residual variances that are constant over time with no covariances among the residuals, then Elmer's good. But if you want something else, you can't use Elmer. Elmer works better with respect to degrees of freedom behaving consistently, though, which is why I tend to try to use it when I can. So we have response time is a function of a fixed intercept and our two fixed slopes. And then we have the contest 1Ds doing the same thing as the other programs in generating a predicted outcome given these multipliers here. So just to reiterate what's happening, the 1 means I'd like one fixed intercept, please. What is the fixed intercept? I don't know yet, but it's going to figure out what it is and start with that. And for the first occasion, I don't need any fixed effect of slope 1, 2, so it's multiplied by 0 and multiplied by 0 for the other one because that's how they were coded. So the numbers that go in these parentheses, the numbers that are literally multiplying the slope variables in this data code, and the numbers that go behind here, they should be the exact same numbers that you use to code the variable. So you're inserting the values of time given your piecewise slope coding that then are going to multiply the fixed slope coefficients stored internally. And then last but not least, here is my request of the difference between the two slopes, where the difference between slopes does not have anything to do with the intercept, which is why the intercept is 0 here. And then I want the comparison to be the first slope versus the second. So the first as the reference for the two. Okay. Any questions on coding? Good so far? Cool. Let's see what happened. So here's my R matrix. We'll do a little review. What's in here? 34,098 is what?
Level 1 residual variance.
Level 1 residual variance. Why are you off your line today? These are the E deviations between the growth trajectory that's predicted by the fixed and random effects and what each person had at each occasion. Our model predicts that they're the same over time. Our model predicts what with respect to the E relationships? What do the blank spaces in here mean?
Nothing.
Nothing. So what's in the model with respect to residual covariance? Nothing. So this is the only type of R matrix you can have in Elmer. That's what I was trying to say earlier, badly, but maybe this is easier just to point. So I call this diagonal. It's called variance components in SAS. It's called independent in Stata, constant variance and no covariance. This is what you have in regression, actually. The idea that your E's are supposed to be independently and identically distributed, that IID thing, that's this. So this is the default in software because this is what you would logically start from and ask, what else do I need in terms of random effects? G matrix. What goes in my G matrix?
Level 2 variance.
Yeah, level 2. Yeah, always feel free to read from the screen. It's always in here somewhere, in most cases. Yeah, I only have one number here, so this isn't really a matrix, it's a scalar. Can I still call it a matrix? Are the math people going to yell at me? No. It's a number, that's what I know. It's one number right now. Why is there only one thing in it right here?
Or not fixed,
Yeah.
constant.
Yes. I'll take constant, but not fixed.
Not fixed.
Yeah.
Random effect, but
Yeah. One thing is
not
random. That's why, because only one thing is random. The intercept is random. And so the end prediction is that this random intercept variance gets stuck everywhere in here, added together, and then you end up with V. The marginal put back together again, and then now the word constant applies. The idea is that this model with only a random intercept predicts constant variance over time and constant covariance over time, which translate into this constant correlation, which has a special name. ICC, yes. Intra-class correlation for now, and in like an hour and a half, it's going to be ICC is item characteristic curve. This is very challenging on me sometimes to get the words right, but we're doing the best we can. So this is conditional. This is an intra-class correlation of the extent of constant person dependency, cough, cough, effect size for constant person dependency after controlling for change over time via the piecewise slopes. So how much person dependency do we have? A significant amount. How much is it? Well, 86% of the variance that remains is because of some people being faster than others. 86% of what remains is because of person mean differences at level 2 in the random intercept. Typically, people don't report conditional ICCs, but because that is sometimes a thing, I wanted to make that connection for you. This is the significance test of that effect size. So the likelihood ratio test that's reported by default in SAS and Stata, and you have to ask for an R, compares your model to an E-only model without any random effects. And then that tells us that this is, yes, indeed, a significant improvement, as you might expect, given how big this intra-class correlation is. Now, our model for the means, fixed effects, right here. You want me to do, or does anyone feeling brave want to try to put the numbers in sentences? Zoomers 2. Are we feeling brave? Sure.
So
That did not sound brave.
The mean for is 191. Yep, that number right there. I can talk.
Big number.
When everything else is 0, so like when both slopes are turned off. Is that
Yep.
the way to say it?
When both slopes are coded 0, which is at what occasion?
Time 0.
Yeah, time 0, which is at what occasion?
Session 1.
Yeah. So it's what I'm asking is, in the coding scheme, where is everything zeroed out? So that's up to you. So we set it at session 1 in the way that we did this. So at session 1, which is time 0, the expected response time on average is 1962 milliseconds approximately. Good. Next one. This is a slope. Someone else feeling brave? I try not to cold call on people, but I will if I have to. I once had a student stop coming to class, and I sent him an email, and this person said that he was terrified I was going to call on him, and that's why he didn't want to come. And so I said, I'll make you a deal. If you come back, I won't ever call on you ever again. And I held up my end of the bargain. So if you don't want to talk in here, if you're feeling shy, that's fine, but that's what the chat window's for too. You can send me a message directly, and it can be as wrong as it needs to be, and no one else will know. So you don't even have to be brave. You're feeling brave?
I can take it. Yeah, of
Go
course.
for it.
To me, that slope represents the average difference between time 0 and 1 in response time.
Time 0 and 1, which is sessions 1 and
Session
2,
1 and 2,
correct?
yes.
Yep, I will take it either way.
That's the average difference, right?
That's a difference, yes, because it's only one change.
Yes, but it is the average or something else?
Average, I would say.
Okay. Yeah.
This is the mean difference between session 1 and session 2, according to this model.
Yeah. Okay.
Mhm. Yeah. So it's a rate divided by 1, or you can just say it's a difference. So what happens to response time between sessions 1 and 2?
It is 163.64 less than
It goes down. Yeah, it declines significantly. So in this context, I would probably want to say that response time improves significantly, because that's what it means to be faster, to have a lower response time. If I want to go strictly speaking based on the sign, I would say response time decreases. And I'll throw the word significantly in there, since we have a wall test that is perfectly fine to use. Now note the difference in the reported degrees of freedom here. The intercept is much lower because it's random. So in Satterthwaite, the denominator degrees of freedom for fixed effects that have a corresponding random effect are going to look more like the level 2 sample size, whereas fixed effects that do not have a corresponding random slope are going to look more like the level 1, which is actually number of occasions minus number of persons minus fixed effects. So that's where this number comes from. There's 600 and some odd occasions. How many people do I have? Should I say that? I think it's 100 It's somewhere near 100. 101 people, yep.
Okay.
So that's where it's approximately 500.
Can you repeat that, please, Lisa?
Sure. So denominator degrees of freedom. The difference in why intercept looks different than the others is because the fixed intercept has a corresponding random intercept with it. And in Satterthwaite, anything that has a random effect, the degrees of freedom look more like level 2. Not exactly, because we don't have 129 people, but more like. This is an estimated quantity. In contrast, these two slopes are purely level 1 fixed effects without a corresponding random part yet. So they get tested against degrees of freedom that look more like level 1, which is the total sample size minus the number of persons minus the fixed effects spent. This is in, where is this is in my book. Maybe chapter 5? That sound right? I forgot. I blanked out on that chapter because it was just too painful to remember. So it was one of the harder ones. Now I'm about to find out if there's a significant difference between expired Mountain Dew and unexpired Mountain Dew. Because this has been in my fridge upstairs for the last 6 months. It's fine. Close enough. My test of close fit for the Mountain Dew has passed. All right. Excellent. Good to know. I've got a Sprite that's even more expired. I'll try that one next time. Good. Okay, so first slope. Response time decreases significantly on average by 163 milliseconds per session, but there's only 2 sessions involved. Okay, who's feeling brave on the next slope? And Zoomers, you can play too. You can talk or you can type to me, either one. You feeling brave?
Maybe.
You can say no.
That is the average rate of change from session 2 to session 6.
Yes. It's the average rate of change per session between sessions 2 and 6. 33 milliseconds a session, yes.
If you were interested to see if slope 2.6 is significantly different from slope 1.2, would you use GOHT or would you use contest 1D for that?
Contest 1D, there it is. So it's estimate in SAS, LINCOM, and STATA, regardless of what proc you're in. And STATA post-estimation, it's LINCOM for everything. In R, it depends on what function you've used, and this one is Contest 1D. Question from the Zoomers.
Hi. Yeah, so that value, negative 32, that's the average mean difference between, I guess that would be session 2 and session 3, session 3 and session 4, 4 and 5, and 5 and 6, right?
Yes.
So you just compare the session and then the session that came after, or the session that came before.
So it is a rate, it is per session, but it's not just using the data from 2 and 6, it's using all the data and trying to draw the best fit line through the means.
Okay, I see.
So yeah, I'd say that the model says that people change on average by 33 milliseconds a session between sessions 2 to 3 to 3 to 4 to 5 to all the way down. If I only use the data from 2 to 6, I might come up with a different answer because it's ignoring all the spots in the middle. Okay, does that help?
Yeah, definitely. So I think I just needed to wrap my head around. It assumes that the changes between like proximal sessions or sessions that are right next to each other is equal. It tries to draw the line through everything.
Yeah, it's literally not different than a slope. It's the change in y for a 1 unit change in x. It's just that we've narrowed x to be sessions 2 to 6 specifically. And so for every change from 2 to 6 in session, we have a 33 millisecond reduction in response time. So putting it together, it looks like people get a lot faster to start with. They don't get as much faster after that. That's a fairly classic learning result. And if reviewer 3 wants to know whether I need a piecewise model at all, do these numbers look different to you?
Yes.
They look kind of different. Is there a way that I could just not stare at it, but maybe like give them some data to support that we need 2 slopes?
LRT.
Oh, good instinct, but we're in REML.
Oh, it's different fixed effects.
Yep, no fixed effects stuff with LRTs in REML. What do I do instead?
AIC.
Difference of
If
Oh,
minus
no,
2
yeah,
log
yeah.
likelihoods off the board, AIC and BAC are 2. What were you going to say?
difference of slope.
Yeah, this thing. I already asked for it. So this is a walled test for the comparison of the 2 slopes. So that number was created in this estimate statement in SAS, slope 2.6 minus slope 1.2, given the direction of the signs. If I flipped where the minus was, I would get the same number just backwards. It'd be minus 130 instead. And in Stata, it's the Lincom right here. The small, by the way, means make it a T test as opposed to a Z test. That's what that does. And then in R, it's the contest 1D at the very end. Question?
So if we used ML instead of REML, could we do a ratio test? Or well, not as B, would they be nested? If you did a model with that, with like the same slope,
Mm-hmm.
and then a model that was piecewise.
Yes, if you
Okay.
were in maximum likelihood, you would have a linear slope that goes through all the sessions as one model versus the piecewise model that has two sections to it. And those are nested because essentially you could view the piecewise model as, what if we constrain both slopes to be the same?
Okay.
And that constraint makes it nested. But because we're in REML, we got to do everything with just the fixed effects. So yes, the way that I would interpret that comparison of the 2 slopes is that relative to slope 1.2 as the reference for the comparison, slope 2.6 is significantly, we got a p-value of over here, slope 2.6 is significantly, how would I talk about it? You have 4 choices.
That's negative.
That's what, yeah, less negative, less positive, or more positive. Those 4 choices cover an awful lot of things. So yeah, I would call this slope less negative. It is less negative by 130, specifically.
So, what's the less negative? Sorry, because I thought that slope 26 was less negative than the other one.
Yes, that's what, slope 2.6 is less negative than,
Okay, yeah,
than
because
slope 1.2.
okay.
Yeah, slope 1.2 is the reference.
Yeah.
Whichever one gets the minus 1 is the reference. It's like getting the 0, but since it's a contrast, it has to sum to 0 instead. So yeah, I would say slope 2.6 is significantly less negative. And I would say it that way because it's not that they start going back up. It's just they don't decline as much. So to put that into English, because most people will be like, the slope is significantly less negative after, what? They don't improve as much after session 6, or session 2, excuse me, is what I would say. They're still improving, just not as much, on average. So then if we look at the predicted outcomes, the difference between the prediction at time 0 and time 1 should be exactly this 163. And then the prediction after that, each of these should be different by about 33 milliseconds, because it's a linear slope. And here is taking these numbers and throwing them into Excel to make a picture. This is what the model says. Pretty good. Now, could I take this second slope 2.6 and add a squared version of it if I wanted to? Sure, I could. I did that in the book. It wasn't significant. But if I wanted to make this second part of the slope here a little bit bendy, because this looks like the middle part's a little bit off here, I could do that. So then that would turn this into still a 2 pieces, but one of the pieces would have a quadratic part to it as opposed to just a linear part. All right, and notice that I've severely cheated the y-axis here so that you could see the overlap here. If I were presenting this picture in a manuscript or a poster or something, the y-axis would not start at 1600 milliseconds. It would start at, either 0 or something that better conveys the spread of response time in these data. Okay, how are we doing? Yeah, so it's not that different. It's just a different type of slope in terms of what it means, but all the rules are the same. How about effect size? So slope 1, 2 and slope 2, 6. Do those talk about change over time or differences between people?
Change over.
Change over time. So given that these are time-varying predictor slopes, which of my two piles of variance should they explain?
1.
Level 1, the time part, right? E variance is variation over time. These are slopes that talk about time. So we should see a reduction relative to an empty model, which is not in this handout, but we had it in the previous handout for comparisons purposes. And it looks like, yes, relative to an empty means model, including these two slopes, explained 24% of the level 1 residual variance. And I have to say it that way. I can't say 24% of the variance because that would be wrong. That would be a marginal interpretation like in regression. I have to customize this to be per pile. That's what the pseudo part means. So drawing a common slope in this disjointed way has explained 24% of the variation that was over time. And in doing that, it made the intercept variance go up a little bit, as to be expected. All right, ready for the next one? So this model says everybody changes exactly like this. Do you think that's reasonable? Probably not. It's an empirical question at the very least. So let's throw some random effects in here. Now here is where different people might take different approaches and everyone could both be right. I'm starting with the first slope. I could have started with the second slope in terms of adding something to be random because they're not hierarchical. My logic in starting with the first one is, well, it's first, and well, that's where the biggest difference is. Like the initial slope is the biggest one, so I thought that's probably the thing that would differ most across people. But I am testing one random slope at a time, though. I could test both at once, but then if I had an improvement in model fit, I wouldn't know which caused it. So that to me is dissatisfying, so I like to focus on one thing at a time. So what is new in my equation that reflects the difference in this model relative to the previous one?
The random effect for the slope 12.
Yeah, this one right here, U1. That's what's new. So how many parameters have I added to this model and don't say 1? 2. You feeling brave? Are you feeling brave? You want to tell us what the second one is? Yes, exactly. The covariance between the intercept that was already there and the random slope whose variance we just added. So the U's belong to the same person. They get to be related at level 2. Would they ever have a covariance with the level 1 residual? No, that's not a thing. That would like break the multi-level machine. Like level means like a separate piles of variance that are not related across levels. All right, so let's see what happened. We have slope 1, 2 now as a random effect, which shows up on the random line. Random line has 2 things on it. That's another way you know that you've just added 2 parameters. In Stata, slope 1, 2 is now after the person ID section here, so it's in 2 different places because it's doing 2 different things. I'm also asking for a likelihood ratio test against the previous model where we didn't have any random slopes yet. In R, slope 1, 2 is right here and right here. 2 different places, 2 different things. And I'm using RunOva to test whether this model improves the fit relative to the one that has only a random intercept. This command actually takes them out one by one and gives you all of the comparisons, so you only just need to find the one that pertains to the slope that you just added. All right, so our R matrix has the same structure, but it has less variance in it. because part of what we were calling level 1 residual, we've now moved to be part of level 2, between person differences and change between sessions 1 and 2. So variability has been reallocated, I would say. My G matrix is a matrix now. Hooray! So now, given that I have slope 1, 2, my intercept is conditional on when that slope is coded 0, which is the first occasion. So this is now the session 1 intercept differences specifically. Here's the variance of my slopes across people, and here's the covariance between them. And I had a note in the previous model, but just to reiterate here, this G matrix should always be left unstructured. So that happens by default in R, but that's something that you have to ask for in SAS and in Stata. The default in SAS and Stata is to not have any covariances among the random effects. But unstructured is the only thing that makes sense, because we want the intercept variance to be whatever it needs to be, the slope variance to be whatever it needs to be, covariance to be whatever it wants. There's no like AR1 or Topolitz or like any kind of patterning to this. Random effects get to be whatever they want. Covariance or correlation between the two is negative in this case. And now the V matrix that we have here has a funky looking pattern. We haven't seen anything like this yet. So is the diagonal heterogeneous or homogeneous? Let's see, he's like, it's funky. That's what it is. Because this part is different, but from there, it's all the same. Because it's piecewise, exactly. So this idea that when you introduce a random slope, you're introducing heterogeneity, but only for the section the slope is for. So 1 and 2 get to have different variances, and they get to have, one gets to have a different covariance with everything else, but from there, it's compound symmetry. So it's like a weird, I'm going to stick with funky. It's just funky. It's not a judgmental term. It's just, it is what it is. But yeah, it's compound symmetry for the part of the model that still does not have any random slopes in it, which is sessions 2 to 6. Here are the 4 parameters then that make up our model for the variance. Intercept variance, random slope variance for sessions 1 to 2, their covariance, residual variance that's assumed to be constant. This is the likelihood ratio test that doesn't help us because it's testing the presence of the entire G matrix, which is not what we want to know. The one that I asked for in SAS, which is provided by LR test in Stata and Renova in R, is contrasting the model. Difference in -2 log likelihood is 63 on 2 degrees of freedom. P-value is 0 to 14 decimal places, so yeah, does help. Let's do the other one. What's new in the equation? We're adding random slope 2, 6. Yeah, what's new though?
The U,
Which U?
U2I.
Yeah, this one. So this model says people differ from each other in how many different ways?
3.
3. They differ in where they start out, they differ in how they change initially, and they differ in how they change subsequently. 3 different kinds of individual differences, 3 different kinds of person dependency operating that together create the correlation of occasions from the same person. That's what this model is saying. How many new parameters are we adding by adding this U2 right here? And don't say 1.
3.
3. It is 3. Because it's the variance of the U2s plus the covariance with the U1 and the U0 that was already there. So now our G matrix is 3 by 3. So slope 1, 2, and 2, 6 on the random line. Likelihood ratio test against the previous model forthcoming. Slope 2, 6 after the person ID to add the random slope in Stata, and then the random parentheses section here in R. That's the random part. Very important set of parentheses, might I say. So our matrix then has less variance in it because, again, we have reallocated what we were calling level 1 residual. Why are you off your line? Oh, because you needed a different line between sessions 2 and 6. My bad. Okay, now I'll give you a different line, and here's what's left. How different are the people in their later slopes? The variance is 2617. Is that a lot? It's a variance. So we'll figure if we need it first, and then we'll try to characterize it. So V matrix now, less funky. It is heterogeneous, but with a different type of pattern from here than here, because these are different variance components that create the heterogeneity. But given that the second slope is linear, it would be a quadratic pattern of changing variance from 2 to 6. And here's the model implied correlations over time, which are heterogeneous given the presence of 2 different random slopes. So now look at the degrees of freedom for all the fixed effects. They match. It's based on level 2 sample size because all 3 of these things are random. Here's my likelihood ratio test result after adding my 3 new parameters. -2 log likelihood went down by 44. P-value is highly significant. What if reviewer 3 says, you should have used a mixture chi-square instead?
It doesn't matter.
Thank you for pointing that out. Please give us a chance to clarify. Because this is a conservative result and it's significant, the less conservative result is going to be significant too. I don't have the cutoff memorized for 3, but I think it's, hang on. It's 7.82, I think, is the regular one, and then the mixture is like 6 something. So either way, 44, way above the cutoff. So yes, it's significant. Yay. Do I need to do like a pseudo R-square for it? No, I wouldn't. Because I haven't explained anything. I have reallocated error to be part of level 2 instead of level 1. So now I know that people differ from each other in 3 ways, but I don't know why that is. So rather than doing pseudo R-square, let's do effect size via random effects confidence intervals. So because I have 3 different fixed effects that each have a fixed part and a random part, I have the potential for 3 different intervals. Yes, go ahead.
I don't know if this helps anyone, but
And you'll be
I
next,
like
Carl.
a very basic function to calculate these. Would that be helpful to share?
Sure. I still throw them in Excel. I don't have a SAS macro for this because I do it so rarely. But yeah, I'm sure there is a way to automate this. Yeah, if you'd like to send me the code, that would be lovely.
Very accomplished because I wrote.
You wrote a function?
That's multiply. That's how it works.
Yeah, that does make you feel good when you get the right answers back. And yeah, if it saves people from typing and the errors that go with typing, good. Question from the Zoomers.
Yeah, so I guess we might talk about this when we discuss the confidence intervals on 1 to 2 and 2 to 6. But if we go back to the G matrix, page 7 here for this,
Yep.
we have negative covariances, negative correlations between our slopes and the intercepts.
Yes.
So does that tell us that like people who start out higher get more better or whatever? I'm
Yes.
having trouble figuring out how to say that.
No, I like more better. That is exactly what I would say. Yeah, so it is tricky to interpret these because you have to think about what being higher or lower on a slope means. And if everybody is decreasing, so I got to do the visual here with my hands, then a high value would be like a less negative slope, and then a lower value numerically would be a more negative slope. So yeah, so if a higher intercept goes with a lower slope, then the worse you start out, the faster you improve. And that makes sense, right? Because people who suck at this have the most room to grow. Right, does that help? Is that where you're going?
Yeah, definitely. Thank you.
Yeah, and then your rate of improvement from the first to the second is not that related, which I think is somewhat interesting. Because I would think that people who improved a lot initially would have less room to change, but that does not appear to be the case empirically. So the trick with interpreting these correlations is twofold. Remember which of them is conditional on time 0 and talk about it that way. So anything involving the intercept, I have to say your initial predicted starting point, because that's what the intercept refers to, is correlated with the other slopes in this way. But then also thinking about what's up versus down in slopes to talk about what high or low means. And that's where the confidence intervals, yes, thank you for that transition, by the way, that's where they can help. So the intercept is fairly straightforward. 900 to 3,000 milliseconds at the beginning of the study is the predicted intercept difference. The initial confidence interval spans from negative to positive, actually. So some people are actually predicted to get worse. And the same thing happens in the latter one as well. And yes, I double-checked all of the math, and this is actually what happened in the data. Some people got worse before they got better. Okay, did that help answer your question? Or do you have another one?
No, definitely. Yeah, sorry, I forgot. to
Okay,
go
yeah,
over
yeah,
it.
that's,
Thank you.
it's funny on Zoom, the hands, when you raise your hand, it doesn't go down automatically, but like the other ones, like the thumbs, they go down automatically, so. But yeah, so rather than have pseudo R-square or variance explained, I would try to phrase slope variability in this way. All right, so this isn't so bad, right? This is like the same thing, just a different type of model family. I'm gonna decide, we have not very much time left. Do you want to look at the next set or just get into it a little bit? And then we'll pick it up next week. So same exact process, changing my coding scheme. So we talked about this at the end of class last time, but just to review. In this version of the coding scheme, I'm keeping slope 2.6 exactly the same as it was, but its interpretation is going to change because it's paired with a different version of the early slope. And I've renamed it slope 1.6 because it operates through all 6 sessions, but last week it was called time. It is time. So I'm putting in a linear slope that operates through the entire trajectory and a second linear slope that kicks in after session 2. Do you remember why I'm doing it this way? What is the purple slope going to tell me in this version of the model? Yeah, there, now it's on the screen. My shameless request for audience participation. Always put the answer in front of them. What's purple going to tell me this time? Yeah. Weather change is different. So think about this from the reviewer perspective. This version of the model directly tells me whether I need 2 slopes at all. Because if one linear slope were sufficient, the result I would get from adding the second one would be a difference of 0. If there is no difference in slope after 2, there's nothing for purple to do. So slope 2.6, when it's paired with slope 1.6 like this, is going to tell me how the rate of change differs after session 2. And this version is more useful if you're interested in a phenomenon that was going to change anyway, and you want to know if change happened differently after some point. And I already know what the answer is going to be for slope 2.6. Do you? It's 130. We already found this. So starting with just the 2 fixed effects and random intercept again, I put the 2 fixed effects in the model. I asked for predicted outcomes. Now note the difference in the coding. Because it's time here, it goes from 0 to 5 rather than 0, 1, 1, 1, 1, but the second one works exactly the same. My things are off. I have to make it match. Same thing in R. Now I do want to point out what I'm asking for separately now. What this model is going to tell me is the initial rate of change and whether the subsequent rate of change differs from the initial rate of change. It's not going to tell me what the subsequent rate of change is. But I put them back together as a linear combination. So time That's the initial rate of change between sessions 1 and 2. Slope 2.6 is going to tell me the difference of how the second slope is relative to the first. So if I add them together, then I get the second slope. So either model can only tell me 2 out of 3 pieces of information. I can get a hypothesis test for the significance of the first slope, the second slope, and whether they're different. This model gives me first and difference, and I got to ask for what second is. The previous models gave me first and second, and I had to ask for what difference is. But they're just rearrangements of the same information. So I asked for that linear combination to get the second slope in each program. And lo and behold, the results are exactly what we would expect. The intercept is still 1961. The first slope, even though it's indicated by time that goes all the way through, is the same number, because it's the unique effective time after controlling for slope 2.6. The unique effective time is only the beginning, from the change from 1 to 2. And here's the 130 that was the linear combination last time. So I would say after session 2, the rate of change is significantly less negative. What is the rate of change? It's minus 163 plus 130 gets me to the minus 33 that we had before. So from the fixed effects perspective, it doesn't matter which way you do it. You can get all the information you need either way. From a random effects perspective, it does matter. The models will be equivalent if all of the effects are random, but what the numbers mean are not the same. So in adding the random effects, the random effect that would go here for U2, it's not going to tell me individual differences in change after session 2. It's going to tell me individual differences in how much the slope changed after session 2. Not individual differences in the slope, individual differences in how the slope changed. If that's what you want to know, this is how I would set it up. All right. And yeah, here's the picture with both equations on it at the same time with the coding there so you can see what happens. Same predictions either way. All right, 141. I think that's enough for now, don't you? Any questions before we call it a week? Yes?
The random effect for the first slope would be the individual differences in change over time.
Ah, I knew you were going to ask me that. Yes. So here's the thing. In this next model, which we're not going to go through, but just to answer your question, what U1 means, like think about just this part of the model, like what's happening on the variance side, and it doesn't have a random slope change. So yeah, this is just going to be a random linear slope that goes through all of it because it's not controlled for the difference after session 2 yet.
Oh, okay.
Mhm.
Okay.
So we have to think about what these things mean in terms of what it has unique, but on each side of the model. On the fixed side, the reason that slope 1.6 becomes just the rate of change between 1 and 2 is because that's all that it does uniquely after controlling for slope 2.6. Because slope 2.6 is constant at 0, 0 during that part. So slope 1.6, that's the part that it doesn't have. But without the corresponding random side, random slope for the second one, then just time by itself it's just a random linear time model like we had last week. Yep.
Great, thank you.
Yeah. Other questions? All right, then homework 3 is out. I checked it in all the packages. Just make sure you read the directions with respect to which R functions you should use for which sections. Let me know if you get stuck on anything, and if you need help, I'll be on email, and I'll have office hours on Monday for any last-minute questions as well. Fair? All right, then that's it. Thanks for being here. see you all next week. Bye, Zoomers. Happy weekend.